Example? I'll repeat it when I ask about that specific thing again. So
you have a global memory which is continuous and shared memory. You're saying you bring a block into shared memory and then?
but it's not efficient. You're getting a contiguous block, meaning that you've stored an array of size 32. Let's think of a warp because block has the same structure. In a warp, there's an array of size 32, and I read that array, and it results in a coalesced memory access, for example, on the global memory, but on the shared memory side, it is inefficient because there is a bank conflict. Okay. So in general, when you declare an array of certain size and you say I'm going to access it using some multiple, right? Every nth based on my TID, right? So every third. It's not always the case that you access things in one contiguous chunk, right? It's not always that the first thread is accessing 0th item and the second thread is accessing the first item and so on. For example, if I've stored XYZ, 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 and I want to read X. So X is every third element. So I'll say I've got an array of floats. One way to do this is to have an array of floats, and I'm reading 3 times my TID. As long as this times my TID is an odd number, there will be no conflicts. And go convince yourself of that. If 3 is 2, no, 3 is not 2. If that multiplier is 2, what will happen? It will go 0, 2, 4, 8. After 14, the address will come back to 0, right? 16th thing is in 0th bank. For 1.x, for 2.x, it's 32 banks, but again, it's 32 times something. So as long as it's odd, there is no conflict. If you're reading a character array, like byte array, then what's going to happen? First says I'm going to read something from 0th byte, 0th location of the byte array. The first one says I'm reading from the first location of the byte array. The second says second location of the byte array. And the first 4 are reading from the same bank. Because the 4 bytes are in the same, it's a 32 big cycle, 32 bit cycle. Okay. So in 1.x, this thing is always in conflict because it basically says you're reading from the same bank, that means you're conflicting. In 2.x, should it actually be conflicting? In 2.x it doesn't, but why? You always read a word, right? The transactions are 32-bit. And so it's not that they're reading 4 different things from that bank. They're reading one thing from that bank. That thing can be fed to all 4 of them and they can take out their section from it, their byte from it. Okay. And so it wouldn't conflict. What about this? Oh, wait, that's not my question. So in 1.x you can make bigger array of bytes and resolve this conflict. And anyway, this is not too relevant anymore because byte arrays are not in conflict anymore. But what about double arrays? If I'm reading 8, double array is 8 byte, right? Meaning each double is an 8 byte entity. So I'm reading 8 bytes at a time. What's going to happen?
Reading from 2 banks.
You're reading from 2 banks. And 16 people are reading, so first 2, second 2, third 2. next 2, it's all fine. But then what happens to the next, the second half warp or second quarter warp? Goes back to the first. Right? So only half of them can be provided their data at one time. What would this access do for global memory? Not a problem. It's 8 doubles, 8 bytes times 16, right? 128 bytes. One memory transaction will read it. Okay, there is no notion of conflict there. In 2.x, it also says no conflict in 2.x, or it says conflict is only for 1.x. Within a half warp, because there are 32 banks now. So what's going to happen? The first will read the first pair, the second will read the second pair, and 16 will read from the 32. So there is no wraparound that's necessary. Okay, so now let's review some of the things we've already talked about. We've talked about the fact that we need blocks to be as big as possible so that there are enough warps. At the same time, you cannot make blocks bigger and bigger and bigger, right? There is a limit. The resource, for example, if they use shared memory, then every thread of the block probably needs a share of the shared memory. Right? So if the block becomes bigger, you probably need more shared memory for that block. And similarly, if there are more threads, then you need more registers and so on and so forth. We've talked about the fact that you can make each thread do more, right? Which is equivalent in some ways to saying that block is small, right? Or effectively you're making the block big. You've set it to be small, but each block is doing more, so in effect the block is big. Can you do that all the way? Meaning, let the block be 32 sized and everything else is getting done in a thread. No, right? Why?
Memory.
Again, memory is somewhat of an orthogonal issue because all that work had to be done. Right? If it's in the global memory, then all these threads, this thread is reading 100 items from the global memory. It's the same thing as 100 different threads reading one item from the global memory. But we need many warps to be active, right? Why do we need many warps to be active?
Hiding the memory latency.
Hiding the memory latency. Not just memory latency, also instruction latency. And that's, okay, it's not in this slide yet. Where did it go? Maybe it's going to come later. The instruction latency is in the order of 20 to 24 clock cycles for most instructions. So while that is happening, if the next instruction meets the result of the previous instruction, then you can't schedule it. So somebody else has to run. And of course, memory has the same thing. If you need the data you have requested from the memory immediately, then you have to wait until it comes back. And while you wait, you want other warps to be able to do something. The general rules of the thumb, you want the block size to be 32x something. It is generally a good idea to start at something like 256 threads in a block. If you make it too small, Why not make the block too small? I have lots of blocks, but each block is small. Same question, right? Why not make it 32 bit? Because then inter-block synchronization is not possible. So you want to make block as big as possible so that they can communicate with each other. Make it as small as possible so that they don't depend on each other, right? And so there is probably a sweet spot somewhere, which is greater than 32 and less than 1024.
So you mean lessen the dependency between blocks? It's okay to have little dependency between the blocks.
No. If you can lessen the dependency between blocks, it's good. But you won't always be able to do that. Right? We talked about in fact, that review will also come. We talked about the issue of parallelism. How do you make things more parallel? Right? Sometimes you make things more parallel by repeating a computation that somebody else has done, and instead of taking that guy's result, you just do your own. Right? You repeat the computation. And when you do that, then you're not depending on somebody else, and you can get rid of the synchronization. They don't need to be in the same block. You just compute your own. Otherwise, you have to sync the threads at that point so that you know that guy's result is now ready, and then read whatever that fellow has produced. So you can, in some cases, get rid of these synchronizations by just repeating some things or reorganizing your algorithm. If you can, good. If you can't, then you have to make your block bigger.
Why not the maximum size block? What is the blocking size?
Maximum sized. As blocks get bigger, they take more resources, right? Moreover, what is going to happen is that eventually blocks will inevitably need some sinks, right? Because that's why they are in a block. They're sharing something. You're depending on that guy to produce something and use that later on. And whenever you have such synchronizations within a block, basically slowly the block swaps start reaching that point and start becoming inactive. I have reached that point. I have to wait for others to reach that point, and I can't do anything until everybody has. So that block swaps will eventually get out of commission for a little while, and if you have nothing else to run, then you're going to go idle, right? And that's why you don't want blocks to be too big, right? And then there are also the issue of resources. If you make it too big, you may not be able to fit all the memory that it needs. Okay, in terms of memory transfers, you would take the copies. Typically, we've seen this, right? You copy stuff into CUDA device, you do the computation, you copy stuff out. What you want to do is you copy all the stuff in one call, copy all the stuff out in one call. So you batch memory transfers as much as possible. And more than that, if you can keep the memory in the CPU, in the GPU device, then you want to keep it there, not bring it back, right? Even if you need, so sometimes you need synchronization across the blocks, and you have to start a new kernel. But that doesn't mean you have to bring the memory back, right? If you can organize your computation in a way that you compute something, you end the kernel, but whatever you computed is still in the global memory. You start the new kernel and just start from the same place. Wherever you have computed, you start reading the partial results from the previous kernel and start working on the next kernel. And moreover, sometimes you would say, oh, this is sequential part of the code. I'm going to do this on the GPUs. I'm going to say if my thread ID is 0, do this. Otherwise, wait. Then I'm wasting a lot of GPU resources. The alternative is you stop that kernel, come back on the CPU thread, you do the sequential part, and then start the kernel again. right? So this will help only if the sequential part is really, really big. If the sequential part was relatively small, like small loop or 5, 6, 10 lines of code, then you would just repeat it on every thread if you have to, or make the threads idle and make one of the threads do the sequential part, so that you don't have to start a new kernel and copy memory back and forth. And also in general, if you can map, right? We talked about the fact that you can map the address on CPU and GPU so that you write on the CPU and it shows up on the GPU, read it on the GPU side. If you can do that, you should choose that, especially if you really have this batched, meaning that you want to do all the reads, all the writes at the beginning on the host, do the kernel, and then all the reads on the host. You're not interspersing lots of reads and writes. Then you want to do it in a mapping way.
The way the system model for map things is weaker. So how do you actually do it? So if 2 pages are synced, then what are we doing this for making sure that?
There is a system thread fence. So you have to be careful about that, and you have to use it.
Is there any specific reason why GPU to CPU transfers have higher bandwidth than the reversal?
GPU to CPU transfers have lower bandwidth.
I thought so, but I just checked those bandwidth. I thought I knew otherwise. Today I checked on some website, it reported GPU to CPU being faster than CPU.
There's something wrong with that result.
So generally CPU to GPU. And is there any reason for that?
The reason is more historic. Typically, graphics pipeline works in the forward direction, and it has been always optimized that way. And so, in order to bring something back, you have to clear some stages of the pipeline and stall, and then say, now get that data back. And in many stages of the architecture, that part has remained. That you have to flush some stages of the pipeline to bring the data back. We talked about the cache line size being 256 bytes, which is actually 128 bytes, right? Because that's how much maximum you can read in one shot. Which also means that I said that the data reads can be 32, 64 or 128 bytes from the memory. It is always 128 bytes if it is cached. Okay. Which means if you need a small section of it, you're doing false sharing, or you may be doing false sharing. Okay, so back to this, the numbers that I was talking about. You take 4 clock cycles to launch all the threads of a given warp on 1.x, because there are only 8 processors and you have 32 to run, so you do it over 4 clock cycles. Okay. It turns out that now with 2.x you can launch it every clock cycle, right? Because there is 2 half warps you can launch, and each has 16 processors. So effectively there are 32 processors to run, and so 32 threads can be launched in parallel. The truth is that it's still done in a half warp fashion. A different half warp is being launched on the second side, on the second group of 16 processors, while as your half warp is getting launched on the first, and then your second half gets launched, and that other warp's second half gets launched, and so on.
Why is it open?
I actually don't know the answer to that. It might have been a more smoother transition from the architecture point of view, from the old architecture to the next. But I really don't know. Sorry?
Just copy one instance of the
And made it faster, right? So instead of doing it over 4 clock cycles, now it's doing it over 2 clock cycles. but I don't know what the logic might have been. You can think of many different reasons, right? You can say that one of the weaknesses of CUDA model is if else, right? Whenever branching happens, there is price to pay. And so they may have figured that all the benchmarks that have branches, lots of branches in them, tend to be slow. And if you make all the 32 warps running at the same time, you are more likely to be wasting lanes, because it's not always, in fact, maybe in those benchmarks it's even rare that all 32 are doing the same thing. Right? So then it says maybe you can break it into two. Okay, that may be one reasoning, but I truly don't know. That's just a pure speculation. To get data from DRAM, it takes 400 to 800 clock cycles, and it depends on whether it's coming from L2 or from the actual memory. For most instructions, as I said, 20 to 24 clocks, meaning that now let's talk from 2.0 point of view. Every clock you can launch one instruction, and your instruction that you launch takes 22 clock cycles. Forget about read for the time being. Whatever instruction you have, general A plus B, register 1 plus register 2, which means for the next 22 clock cycles, if you need the results of this instruction, you are out of commission. So every warp is out of commission for 22x its instruction count. Right? If it's got 100 instructions, it will run 100 clocks, but 2100 clocks, it's actually going to be sitting, doing nothing. So you need that many extra warps just to fill, even if you're not doing read accesses. So the minimum number of warps you're going to need is in that order, 22. Probably 32 is a better number. And every time it goes to read now, it's going to wait up to 800 clock cycles. Now you need 800 warps. That's too many. Okay, but that is the level of parallelism that you're going to need. Of course, you don't need 800 warps, because nobody said that you have to run other warps only once. You know that every warp can be run every 22 clock cycles, and if you have to wait for 800 clocks, then other warps can be run every 22 clock cycles. Hopefully they don't have read-write instructions. Okay? So there is this notion of your compute density, which is the ratio of how many instructions you have of the 22 cycle variety versus how many you have of the 800 cycle variety, the reads versus computes. And you have to have at least that many warps, and probably many times more, because many of them will also have downtimes. They can't run because they are depending on something else. Okay, we talked about memory optimization already. So some of the other things that you probably need to be careful about. One, very often you will realize that you have local variables, right? The automatic variables, auto variables, in the thread local memory, meaning they are taking 800 clock cycles. What could have been taking around 1 clock cycle. You probably want to be especially careful about and you want to check that you're not going into thread local memory. And there are ways to check, right? You can give the PTX compiler verbose option, and it's going to tell you. As it turns out, PTX compiler is not the end all, right? Because at the end, PTX code, which is architecture independent, is further compiled. And if you are running on an older architecture, then PTX's guesses about how many registers you have may be out of date. In which case, you actually, if you want to be doubly sure, you inspect the binary object to see whether local memory is being used. Okay, it's possible, right? There is a CU obj dump that comes with CUDA SDK, and it will tell you wherever it will give you the assembly language dump, and you can do a grep and see something .local, and you know that things are going into local memory. Okay.
Could you disable it to compile it into a code which goes into local memory?
Meaning never go into local memory. It's not always possible. Right? If you have so many different live registers in your code.
Yeah, it will give a warning that I'm going into local.
Yes, I in fact think that should be there. It should by default give you that warning, and for some reason that's not there. But you can get this information out. Okay, so I'm going to stop here. This is basically all about CUDA that we are going to discuss in class.
One very remarkable thing about NVCC is that if you do NVCC on the same file without changing it twice, it deletes.
On the source file?
Yeah. It deletes. I can reproduce it. So if I do NVCC minus keep, which says keep all the intermediate files, and you don't change the .cu file, but you change your driver code or whatever, and you make it again, and NVCC gets called again, and then it deletes.
That's a bug that you should report.
It deletes the file.
That shouldn't be happening. In fact, I have never heard, not that I have done that myself, but
That happened with me.
that's odd. But maybe you should report that bug. If it is reproducible every time, then that definitely should be a bug. Did you try to do it on different machine maybe? Sheshna. Because it's possible that there's something wrong in that. On your laptop also. Then that's an NVCC problem. So you should definitely report that. Let's get back to the algorithm about that. I'll show you what that algorithm. Now we are switching back to in some sense, continuation of the algorithms section that we were originally starting with. And this is the question from yesterday's quiz. Right? We want to find in a vector of length n, 1-bit vector, or 1-bit element in this vector, which is the first. Okay, this is not that hard to do. If I told you you can have n squared, you can have n squared work one at every 1 or 0 at every vector position, and I want to know which is the first one.
Are there then we have another 1 to 0? We have only one in the whole sequence.
Pair 1 with every sequence meaning exactly?
I mean, just like we did in MinFind, we did comparison of one element with all the other elements. So if there are 2 elements which are 1, then we set second element to 1.
Right. So for every element, I want to know if I am the first one. To know if I am the first one, I'm going to check if there is any one on my left. So if I have n processors assigned to me, then I can figure out if there are any ones on my left. Right? How? How will n processors figure out if there is any one on my left? So I only need I processors if I is my index. So the other n minus I are extra. I processors, one allocated to each position, and I want to know if you are a 1, you are a 1, you are a 1, you are a 1. Any one of you is a 1. That's an OR. Right? So all the I other processors allocated to me can tell me whether I am the first one or not. If I am the first one, then I raise my hand. How many people can raise their hands? Only one, right? Because there is only one first one. So order one time n squared work is straightforward. How do you do this? If you want to do it in order n time, order n work, order one time still. You divide it into root n blocks, root n size each. And within each of these blocks, you can now do this in parallel, right? I can assign.
Can we do it like cascaded type? So let's call this algorithm root n algorithm as A1, which does it in order n time.
We may not need that, right? If we can do this in order n work, order one time, then cascading, well, it's almost like one level of cascading.
The smaller problem is simpler.
The smaller problem?
The smaller problem is the non-working. It's simpler than division. You just need to find whether these smaller moving blocks contain a one.
Contain a one or not, yes.
That's very not problem.
Yeah, but in this case, it's simpler, and that's why so that's your argument, that you don't need the full cascading. Yeah.
And what we just like that, because you can divide into root n, and in a new array of root n, so the processor would write their index if it is 1.
If it is 1, at which stage? Because all the processors are, many processors could be 1.
Yeah, so anyone would succeed, right?
Okay.
Yeah, arbitrarily
Anyone would succeed. So the first block would write the first position of the array, the second block in the second position. So this is the second one value would be greater than 1 if ones are in both of these.
No, restart.
So you have this original array.
Yes.
So it's indexed from 0 to n minus 1.
Right.
So if the processor sees 1, so you have root n blocks.
Root n blocks.
So the first block would write at the first position of the array.
First block. So you also have root n processors for the root n blocks.
Yeah.
Root n block.
Each block has root n processors.
Okay.
Now I have a new array of size root n. So the first block would write at the first position, the second block the second position. And what the processor writes is the index at which it is 1.
Index of the first one.
Index of if it finds that the value is 1, it writes the index.
But there are root n processors accounting for that root n block, right? So one of them is going to succeed.
Yeah, one of them is going to succeed, but I can be sure that the value written at the second in the new array, the value written at the second index is greater than the first index.
Yes.
So then I can apply min find in this using all the n processor in this root n size. So I can know the block.
Why do you need to find min find? You have the indexes, you know the first index is the min.
No, but it might be possible that the first block doesn't have a 1.
So nobody writes. So you have to write a large value
I
there.
write the maximum in possible. I initialize it with that. I find the min find, and then I know the corresponding block, and then again all the n processors in their root n.
But mean finding is not order 1.
You are using n processors in root n.
You don't need min find, you just need the same thing. The first one in the small root n array.
I'm not writing the 1, I'm writing the index. So
You write a one.
Anyway, that can also work. This can also work. In order n time, with constant amount of work, we can figure out which is the first one. How does it help us with finding the prefix minimum?
So here, input end of the processor.
Where? No.
Because for one block of length root n, there will be n processors involved, and there are root n such blocks.
Wait.
I mean, the original algorithm you told that for an array of length n, there will be n square processors involved. Right? So for a block of root n, there will be n processors involved, and there are root n such blocks. So n root n processors are involved.
Did I say something incorrect?
At the lower level only root n processors are required because we are just checking if it is a 1 and
We are not finding the first one in the root and block.
This was initiated from the original algo, which n square processing or array.
So first we divided into root and chunks, and when in each we just solve the problem. Is there any one in these root and
Okay.
and not what if
Okay, so how does this help us with finding the prefix, or does it? If you were to try, again, think back in terms of finding prefix minimum, what do you need? And did I say what our target is? Okay, it's okay. So yeah, our target is log and time, just like for min. Although we can do better, but that gets a little complicated. Log and time with n log and work.
Wait, so can you do this in n square work on the order?
Yes, you can. But
the same technique in this fashion.
here it was only a matter of finding any one, right? So you said root and blocks, I gave you root and processor each, and you can figure out the OR of whether you have any.
So over here,
But you don't get that facility over there.
over here also the sub problems that we divided are simpler than usual. In the sense that now I only need to find the minimum in each block rather than the prefix minimum for each.
Okay.
So if you find the minimum, that you can do not n work and not n. So you have the minimum for each of the root and blocks. And now consider these root and minimums and find the prefix minimum on this in n square work and other one odd log.
Yes.
And now you know the smallest element in the first I minus 1 blocks if you are the ith block.
No. So how have you figured out the prefix minimum of a group now? Of root n?
N square block from other log.
Are you dividing it into root n just like we are here?
Right.
Okay. Then how did you get the prefix minimum from root n? There if you do n squared, then it is n root n.
No. So over here I just find the minimum in each block.
But how do you find you need the prefix minimum for every element?
Right. That will come in the next step.
Okay.
Yeah. So you have so step 1 is divided into root n blocks of root n size and find the minimum in each block.
Fine.
Now consider an array of the minimums that you have found, and that is the root n size array. And find the prefix minimum of this array. So now the ith position will have the prefix minimum of would be the minimum of the first I minus 1 blocks of all elements I minus 1. Now put this element along with the root n elements of this block and
You're going in the right direction, but there's some.
minimum for this array.
How?
So we got the root log, and I consider this block and there are root elements in this, so root and process can compare it with.
There is a little. That's where there is it.
Instead of this root n side chunks, can we initiate with log n side?
Log n size chunks. It won't lead to the same efficiency. It's possible. It will bring it down.
Again means the recursion.
So let's not. So that's enough discussion, and the good ideas there, and we'll see that there are some of them are being used here also. But let's go through. I had mentioned this secondary problem also, and it is going to be used kind of as a subroutine over here, but it is also something that will be handy for many different algorithms. And this problem is called all nearest smaller value, meaning that for every element, I've got an array of, let's say, integers, and for every element I want to find the nearest to my left or right, doesn't matter, nearest to my left which is less than me or greater than me. Right? So you can formulate it in one of those 4 different ways. So let's, for concreteness, say I've got an array and I want to know for every position, I want to know the nearest element that's less than me to my left.
Can you reduce it to a first one problem by subtracting myself from everyone?
Very much. Right? In fact, that's what this is shown over here in this slide. You basically say, again, for every element you assign n processors, I processors for ith element. And I want to know, for me, the I processors will tell me which one of them is less. Right? I want to find the nearest one. So if the ones that say they are less write a 1 and the remaining people write a 0, then I am looking for the first one on my left, right? And that, given I processors, I can do it in order I work, order 1 time, right? Or everybody is doing it in parallel, right? Not much communication across the elements. So every element has n processors, with n processors or I processors. With those n or I processors, with order I work, order 1 time, it's going to determine its nearest left. Okay, and everybody does that. So n times this I, or rather I1 plus I2 plus I3, and so order n squared work, order 1 time, you can find your nearest left. Okay, how does that help us with prefix minima? This, by the way, is in some sense a competitor to an algorithm that was just described, where in order n square time we can find the prefix minima. This is only finding it in order n square time. So what's prefix minima again? For every element, I want to know the smallest of the people on my left. How is this related to the previous problem?
First one,
No, the all nearest smaller value.
There we stop as soon as we get the value smaller than me, and here if I get that value, from this value I'll be comparing further whether any value exists.
It's an even more direct connection than that.
So the smallest value is the minimum value.
Not the minimum of everybody on my left, right? It's the value that's less than me, the closest such value. There are some of them, they are more than me, some of them are less than me. Among the ones that are less than me, I want the first one.
I can jump from these values, right?
Won't be the answer minimum in every case. The minimum value in the whole array.
No. If it is sorted increasing order, then the next element will be your all nearest neighbor. Everybody's next element will be the nearest neighbor.
My or nearest nephews.
It will be the answer for my audience.
What will be the answer for
My
mine?
answer would be my audience is answer.
Recursive. Yeah, but there's a more direct connection.
We can do it sequentially, then there is.
Actually, it's already on the slide. We're not actually going to jump. But if we can, remember this is being done in parallel, so they can.
Recursive version only. I mean, it's the same.
It's not a recursive version at all.
I mean, you go on.
No. There's no go on business here. Right? Definition is that I've got some things on my left. Right? I'm going to find everybody's nearest neighbor, all nearest smaller value. Right? One of them is not going to have anybody on its left.
That's what you want.
Right?
That's the minimum.
That's the minimum. Right? Because everybody on its left is greater than it.
So that is where the recursion.
There's no recursion.
I mean, the conceptually, the recursion.
If you think of it as a sequential process, then yes. But in parallel, I'm just looking, I can throw a bunch of processors. There's no dependence among this guy and that guy and that guy and that guy. Right? Whoever says that there is nobody on my left wins immediately. I don't even have to wait for other people's answer. So there is no recursion per se. Of course, that's maybe one way to compute this when you're doing a sequential computation. But in parallel, that's not necessary. So that dependence is not there. Okay, so just for instance, A is the element we are interested in, and M is the element that has nobody on its left, which is smaller than it. Right. So when it computed all nearest smaller values, it got itself or it got null. Yeah, depends on how you actually implement it. But it knows that there is nobody on my left, either because it found its own value or because it found a null. What if there is a element B in the middle, which is smaller than M? Could it be?
And we are taking the largest chain, and B can be smaller.
No, I'm asking, is such an element possible where B is your prefix minimum? But we do know that B has an ANSV, right? It has a neighbor. If B has a neighbor, then there is somebody that is smaller than B. Any element to the right of this one we found cannot be the prefix minimum for me, meaning the smallest element to my left, because it has a smaller element to its left. Right? If B were the smaller element, then I couldn't have found something smaller than it on its left. So anybody to the right of M has a smaller element. So it's not possible that one of them is the prefix minimum. Can anybody to the left of M be my prefix minimum?
Because M has no.
If anything to the left of M were smaller than M, then M would have found it when it was doing ANSV. Right? It wouldn't have said there is nobody smaller than me to my left. So the leftmost element, which claims that I don't have an ANSV, is your minimum, is your prefix minimum.
Repeat the right of M element to this argument.
The right of the argument. Anything to the right of M, for example, in that slide there was an element B, couldn't possibly be the prefix minimum, because if B were the prefix minimum, you would have found another B prime which is less than B. Because B has a smaller value to its left. Right? Because B has an ANSV.
Property of M is that it is the leftmost element which does not have an ANSV.
Which means people to its right have ANSV.
M is the leftmost element which did not have an ANSV. So elements to the right of M
Have.
Is the rightmost element to the left of A which doesn't have a ANSV.
M is the rightmost element on left of M.
M is the leftmost element.
If it is the leftmost element which does not have an ANSV, then elements on the right of M can have and cannot have an ANSV. If it does not have an ANSV, then M is still the leftmost element without an ANSV.
No, the thing is, if B doesn't have an element to its left, wait, no, they're not in a decreasing order. So the largest index is the rightmost element, right, which doesn't have an ANSV.
The rightmost. Yes.
And anybody to its left cannot be, for the same reason. It would have found its ANSV. How long does this all take?
How do we know which one is the largest?
Yes. How? We've just done that as a subroutine, right? Exactly. For me, I'm going to ask everybody who of you has an ANSB, right? Some of them will have it, some of them won't. They'll write their ones and zeros. I want to find the rightmost one which had no ANSB, right? So if you didn't have ANSB, you write a 1, then I'm going to find the rightmost one. All right.
There will be always one element who is writing this.
One element will be writing what thing?
That I don't have any.
Yes. No.
But that is what I want to know. Because anyone else will have an element.
Suppose it's sorted in decreasing order. And so everybody to your left, for everybody, is greater than you. Right? So there's nobody less than you on your left. Okay. All right.
Isn't this part simpler? This problem simpler than the first one, in the sense, if
The minimum, finding the first one.
finding the largest index, which has A and SV, largest rightmost index which has A and SV, isn't this problem simpler than finding the first one in a bit stream? Because if you had n processors and n bits, then each processor would ideally have to check all the indices before it in the first one problem. But here it knows what its A and SV is, so it just has one value, null or whatever itself. So it has to check only one value, not I values. To
Why?
find out.
How do you know? Everybody has written whether they have ANSV or not, right? Some of them have, some of them don't. Okay, so it's same problem. Some of them are ones, some of them are zeros. Now you want to find the nearest one, the first one that said, I don't have it. Okay. Okay, so now we are going to take a break.